Okay, once again, here we are. Let me copy the video link and put it over in here. Got Discord happening for everybody, just in case. Hello, everybody. How's everybody doing today? It's election day. It should be a holiday, in my opinion. But since it's not, we're here. And we'll do our thing. And hopefully you've all, let's see, I'm going to make sure to close that window. Got the live stream going on there. Having some tea, trying to relax, and this existential dread and wondering about how this election is going to turn out. Hopefully all you've got out there voted. Who knows? This could be this could be a real, down to the wire and beyond sort of thing, counting every bean and counting every vote and all that sort of thing. So we're going to try to keep things light today and still do some cool stuff. So I put some, I don't know if we'll go the full time here. Maybe we'll just, kind of do the fun lecture piece. And I did put a video. If you look in the Discord channel, I posted a link to kind of like a walk and talk through, and we'll do it again. So if you're tuned in here, you can decide, if you want more detail on my project, basically where we were last time. And let's see, that was let me open up a Google Doc here because let's see, where was that one? The fantasy-based game. Here we go. So today we're going to talk about a bunch of things, a bunch of really cool and important things. Oh, let me start the recording just in case. And bunch of topics, specifically smart enemies, right? The enemies in our games now are going to be smarter than the apples that are dropped from the trees and things that just went back and forth. We're going to talk about how to really get the enemies to see the player and interact and kind of feel like they have, some smarts behind them. It's going to be like not really, really smart. We're not talking about neural networks here or even, Markov chains or modeling and all that kind of stuff. It's really just some basic spot the player. If you can see the player, make some decisions. It's a very algorithmic process to kind of make it feel like, yes, I'm being chased. Yes, there's something happening in the game. It's not just a bunch of dumb, obstacles that you have to jump over. Maybe some of that as well, but we're going to try to make the enemy look or feel kind of like it's doing a real thing. And we're going to use a couple of techniques. There's a thing called raycasting, line casting. There's other casting. We're going to use actually circle casting as well as another topic. Mention that maybe briefly in some of the other stuff. And also the use of dot product, right? So one of the big math things, dot products and cross products, two of those math things that turn out to be really useful as far as game programming goes. Two of not the most complex topics that every game developer should know about, but two that everyone should know about. Not the most complicated ones. But anyway, let's talk about what they're going to be for. Now, all right, let's look at, we're going to go back over to, and we're going to talk about the game as it is so far, or kind of what I've been working on so far. See how maybe it's sort of matching up with where we're at so far. So this is where on I think it was Friday, we decided by committee that we're going to do sort of this fantasy-based game. With the hero is going to be this Link type character, and he's from Tiny RPG. We're going to have some hearts that keep track of things. The setting was going to be a dungeon. There's going to be some ghosts, maybe skeletons, bandits, goblins, something like dungeon type enemies. The ghost floating around randomly shooting at the player, perhaps. Maybe limited to left and right and float motions. The bandits would move smartly and chase, even though they were sort of kinematic objects. Attacks, WASD move, mouse, aim, fire, arrows, power up, triple fire at angles. These crazy ideas. Multi-attacks, not quite sure what that even meant. Enemies. So it's sort of a boss thing, some kind of energy ectoplasm firing something or other, and bandits that would somehow throw knives or axes. And we're going to have some environmental hazards, maybe a spike pit, some kind of robo-type enemy, maybe, whatever. An arena, which waves come in and spawning a few enemies at increasing speed. So here's what I got so far. Okay, so I got a little sidetracked in some different things. And I decided I would do some of it. I was going to challenging myself, do some in Bolt and then some in C#, so we can talk about different ways. And I'm going to kind of step through as we talk into the smart enemies specifically as we go. And I'm going to probably go ahead and do it in C# today to kind of let you know how that is. But you can do any of these techniques you can do in C# or in Bolt. I found it kind of fun doing it in Bolt because it's just like, real quick grab, put some objects in, paste them in and see what they do. And then every so often it turns to spaghetti. So this is what you got to worry about when you're programming in Bolt. That's the one problem with most visual programming languages. Code can turn into literal like spaghetti on the screen, and you'll see why in a minute. Okay, so if you want to watch, I did a whole 27 minutes, I think, 27 to 30 minutes about why I would only give myself a B+, maybe a C-, or no, C-, maybe a B+ in this game. So I'm a harsh grader to myself, thankfully for you guys. I might not quite be as harsh on you guys, but anyway, talk about the reasons why I don't consider this to be certainly done yet. This isn't complete, but it demonstrates a lot of concepts and things. We'll dive right in. All right, so hit play. First off, there's no sound in the game, which is a bummer. So that's points off for that. Let's see. Hopefully, I don't know if this is going to load directly into. I want to do maximize and play. So you can see, oh, okay, you can't see it. All right, let me do maximize and play here. And we'll kind of play through a little bit to show where we're at. So on the screen, we have, and I'm going to be hiding in this bunker. There's sort of a bunker in the middle of the screen. That's what I just refer to it now. We sort of have a bunker in the middle of the screen. And already some spiders are guarding the exit. Oh, and a goblin type of guy there. So we shot him. Whoops. So there's a lot going on, lots of craziness going on here, and it's just the start of things. It's still, like I said, this is sort of still at prototype phase, but I've got the player, which is sort of a WASD, move around type of thing. Oh, let me change the scale here so you can see everything that's on the screen. So the player here, there are these spider enemies. We're just crawling all over me at this point. There's a heart meter, and if I get hit, you'll see the heart kind of goes down. I don't have 3 hearts, but I do have, you can go down. I think it's like 10% each time. There is the ghost king who goes whipping around the scene here and is firing at 90-degree angles at a certain rate. And the cool thing I found, what I thought I kind of liked about the results, is he flies around, and you notice he does face a generally correct direction as he goes back and forth. And he's shooting all these things. He kind of forms this kind of bullet maze. So it has a nice kind of bullet hell kind of feel to it. That, if you are running around, you can kind of try to dodge your way through the bullet maze that is formed. And you can even set up these sort of invulnerability moments using this invulnerability thing where all of the bullets can kind of bounce off you. Let me get back in the bunker. Okay, back in the bunker. So we have the ghost who flies around shooting stuff without any real intelligence. He's just flying around shooting stuff, but still kind of a cool enemy. We have the spiders and the goblin, rogue, orc, whatever you want to call them. And they are, at this point, turning out to be this sort of smart enemies. So they move around very similar to the player, and they even have some animations going on them. And they have a combination of motion. You'll see that they do kind of wander around on their own if there's nothing going on. But if I get out there, and whoops, I pushed him into the wall. That was terrible of me. If you'll see the spider in certain circumstances. Oh, I should have. I need more goblins. They're cooler. They will actually chase the player. If they see the player, they will chase down the player. They're awfully dumb now, though, and the moment they collide with anything, they die. So they're not particularly good. But here we go. You'll see that they are, in fact, chasing. And so they will follow and try to get there. And they will animate in the right directions and things. And the moment they collide with anything, they die. So they're kind of dumb in that way. They don't fire anything yet. They are vulnerable to my arrows, so I can shoot my arrows at them. The Spiders, however, the spiders don't have any colliders on them yet. So they are kind of smart in that they will chase, and you'll know that they're chasing you by when they follow you, they will change direction. So they're kind of funny in that they're just aimlessly wandering around. They don't change the orientation of their animation. But when they are being smart, they actually face you and chase you down that way. So we got some smart enemies. We have a couple of different power-ups. There is now first off, we have our main weapon is an arrow. And the arrow is kind of cool in that we aim it by using the mouse. So it's kind of a WASD aim and shoot kind of thing. And the other special thing about the arrow is that the speed of the arrow, you'll notice if I shoot them kind of quick, they kind of, they just, kind of nice and slow. If I hold down the button, the mouse button, you'll see that the arrow eventually kind of pulls itself back far, and then it shoots rather quickly. So if I have the time to spend, I can like power up the arrow and shoot it really fast, or otherwise it's kind of slow, which is kind of cool. Then I have the coin. If I grab the coin, and the coin doesn't disappear, but the coin is there, and then it becomes a three-way arrow sort of thing, which was something we wanted. We wanted a life power-up. So you see if I touch the life, I gain back, I think, a quarter of a heart at this point. And then, whoa, yeah, I forgot about that guy. The mole is really, really dangerous. It's kind of the moment the mole sees you, it just totally runs you over. I forgot about that guy. So that's it's sort of taking shape. Let me restart here just to show you the other power up, which is the invulnerability kind of thing here. If I can escape out of here. Yeah, I don't die if I run out of hearts. That's the other kind of, like, I become invisible, and then while I'm invisible, you'll see that I repel everything, and my arrows shoot really fast while I'm in that mode. So a bunch of things going on. The environment is pretty good. There's some spots you can hide behind. You'll see there's like this corner thing. I can hide behind the corner. The original screen was really just this part here, and I decided I wanted it to be bigger, so I opened it up, and I can hide behind there. I can hide behind these big, whatever they are, column wall things. And I also can hide behind, let's see, here's a good case. Let's see our little goblin guys chasing me here. And the problem is, okay, I get behind here. They can't see me anymore, which is why they didn't chase me. If I come here, now you see that they will chase me. If I move here, he might bump into the wall and then die. But so there he is chasing me. And you can't see me when I'm behind there. Oh, you can hide. Now you can see me. Oh, and then he died because he bumped into the wall. So a lot of things going on. I think if I polished it up, yeah, I could, get to an A. But I don't know. What do you guys think? What would you consider? What grade would you give me on this one? We should take a vote. Let me pop out. I have my volume way too high. Whew. It was terrifying. It was the loudest B I ever heard. You're that excited about what was going on. All right, fair enough. But there's a lot of things in here that there's no sound. A lot of the colliders aren't quite worked out. Obviously the spiders are kind of halfway done. Bunches of things kind of left open. But I think it's off. At least in terms of, I have a roadmap, right? I had my model here, my plan, which set forth some goals, and I'm well on my way. I've touched a little bit of them. I've created what I call a vertical, or what is called sort of a vertical slice, right? The personality of my document is now kind of really coming through. I've got, more or less bits and pieces coming on here about what's going on. Maybe the environmental hazards, the spike pit kind of thing, not quite happening. But everything else, we got the start of some things. The melee attacks are just really going to be like, when you're close and all that. Some of it is just dependent on finding graphics, and I'm probably not going to get too carried away on that, and you shouldn't either. But a lot of the mechanisms are there, which is really good. So that's, I think, I would agree. I think maybe it's a B based on the mechanisms. I just really need to polish them up, get them working, and so on. So that's where that's at. So with regards to today, the big thing I wanted to talk about is how the enemies are sort of wandering around, how they move, how they detect the player, how that sort of makes sense and how they would. And also another kind of cool thing that makes them smart. And let me do this. This should be fun. I'm going to tell it to spawn a whole lot of enemies. For some reason, it's better at spawning spiders than it is at orcs for some reason. Maybe there's a bug there. I don't know. All right, so I'm going to try. You'll notice it actually doesn't generate 100 of these, but it basically, there's a chance that we'll have 100 of each enemy. And so let me go ahead and press play here. And the other cool thing about the smartness of the enemies is that the enemies will not appear on top of one another or on top of an obstacle, right? So even when they're spawning, they have a little bit of smarts to them, right? They're going to appear within a certain region of the screen, and they're not going to appear on top of one another, right? So, well, the spiders are allowed to appear on top of one another. I lied, but they didn't appear on top of any of the goblins or other pieces, because the spiders, that was the one bug, the spiders don't have colliders on them, which is why they are invulnerable and why they can, once they're on the screen, you can have other things on top of them. So that kind of makes them weird for now. But it did distribute themselves pretty well. Wow, that's bona fide scary. These are great spider art, if I do say so from my own choice. Not that I made them, but they look cool. But they're spawning in such a way that they will not be on top of obstacles. They'll be, in free game area, and they shouldn't be on top of any other characters or anything that has a collider on it. Right? They avoid colliders when they're spawning, which is kind of cool. I think that's kind of important. Otherwise, the idea is like if you spawn into a game and you immediately show up and everything blows up, that's not cool. So it's nice to generate the world in such a way that it doesn't blow up on itself. All right. So let's look at the spiders, or not the spiders. Let's look at the notion of a smart enemy. All right. So let's jump to the presentation. We actually have, I do have some actual presentation bits about this. All right. So smart enemies. And the main thing about creating smart enemies is saying, okay, when do enemies see the player? When do they take an interest in the player? That's sort of the main thing. And what do they do as a result of seeing the player, right? Do they chase? Do they shoot? Do they do whatever? All right. Now, before we get into that, in this material, also had in this particular presentation talked about another type of movement. We're not going to be showing this in this, but it's worth knowing about the tank style movement. I'm not using that in this game, but I wanted to have reference to it, so that's going to be there. Won't worry about oh, why did that go? Let me try that again. Oh. Try that one more time. All right. Do I not? My presenter mode. Okay, so that one. All right. Now, so two important concepts with regards to the enemy's ability to sense the player. The first thing we'd use is this thing called the dot product, right? The dot product is a way of sort of comparing two vectors. We do the dot product of two vectors, and we get a scalar, which sometimes is referred to as the scalar product, the dot product or scalar product of two vectors. Now, I use this quite often to look at, to create, it's useful for getting a broad sense of what can be seen from a particular point in the world, right? What a broad sense of what can be seen. For example, establishing sort of a field of view for a NPC or a character or even the player. You can do that sort of thing. So you say, okay, I need to establish the field of view of the player. And so what I do is I have a known object And let's see, this is one of the good cases where I will do some drawing on the screen now. And the idea is for a dot product, what you do, I'm not going to show you the math on here. We'll leave that to your math books. But since there's a built-in dot product, we're just going to use this. So imagine we have the NPC here. We have an NPC and we've got the player up here. Everybody see that one okay? That's working out? Read that okay? Okay. So we have the NPC and we have the player. Now, the graphics for this NPC, we're going to assume that we have some animations, and so we know the NPC is walking up, or the NPC is walking down, or the NPC was walking to the right or to the left or something. We have basically a motion vector one way or another for that NPC, right? We have some, basically, the direction in which that NPC is looking. Maybe by default, it starts off being that the NPC is looking in this direction or whatever. And then, as it moves, we say, okay, it's looking in the direction that it's moving, something like that. We can use that as the direction, the look direction, right? Depending on how we're handling our graphics, it might also be, the look at, or the up or right or left or whatever sort of direction. So we're going to have some way that it is facing, right? And the challenge is to say, okay, the direction that it's looking in, let's say it was looking in that direction, versus the location of the player up here, right? So we know the relationship of the player and the NPC. This is just potentially another vector here. We can say, okay, this position and this position. We can subtract the player position minus the NPC position. That gives us a vector. That would say, okay, if we added that to the NPC's position, it would get us to the player. So there's a vector that we can create. That's one. And we can compare that to this look vector. Okay. So what a dot product sort of does is it says, okay, how similar are these two vectors, right? If they were perfectly aligned, so if the NPC was looking in this direction already, the vector, that was one vector, and the other vector was this one up here, right? They would be perfectly aligned, and that would be a good thing as far as the NPC goes. The NPC would definitely see that player. Whereas the moment the NPC was like, looking, in sort of this whole arc here, that's sort of looking in the opposite direction. That'd be good to know. That's like, okay, the NPC is looking backwards or looking away from the player. And that's basically what the dot product will tell us, okay? So when we have the dot product and there's nothing in common here, basically this one is not contributing, the Y component wouldn't be contributing anything between this vector and this vector. That would be this case here. It would be 0, okay? When they do have some amount in common, right, this one could potentially project itself onto this one by some amount. That would be positive. That would be this one here. So it's greater than 0 when in front. So here is greater than 0. Here is equal to 0. And behind is less than 0, right? So it's less than when behind. So this is kind of cool. We can use this dot product to figure out kind of generally where that's facing. So this whole arc here is greater than 0. And we could even make that tighter if we wanted to create a field of vision. What I normally do is I create something that's like about, this area here that the NPC needs to be looking within a certain amount to see the player. So I might set a threshold of like 0.9 or 0.8 or something like that to say, okay, it's not good enough that it's just greater than 0. It has to be greater than 0.8 or 0.9 because I want a tighter field of view, sort of thing. That's what happens here. So the dot product is what we can use to do that. Now, one other thing to get this to work, to get this magic to kind of happen as accurately as possible, we also use something called normalization, okay? So what normalization does is it takes any vector and it sets its magnitude to 1, right? So that when things overlap, when things point at, directly at each other, that is 1, right? And everything will be between 0 and 1 and 0 and -1. So we deal with normalized vectors so that our math, our comparisons wind up being pretty easy. All right, so here's the kind of a coded version, a slightly coded version, where we said, okay, here's our target, right? Our player, we'll call it the first part here. And here's our NPC. And we subtract the two and we get this vector, right? This vector that I pointed out over here, right? And then we take that vector, the normalized version of that vector, and we do the dot product of that with transform.up. Now, transform.up just happens to be, according to this NPC here, this direction. All right, so assume that this NPC is looking up, right? And for a tank-based controller, if we had, just you actually were rotating this thing, transform.up would always be pointing forward, and it's actually a good candidate for the direction that the non-player character is looking in. Transform.up is a like I said, pretty good candidate. If you can change the direction it's looking in, say like you have the WASD keys and you can point up, down, left, right, you may need to keep track of that look vector, that whatever it is, instead of transform.up, you may have to keep track of that and then compare, right? So if you press the W key up, set your look vector to be up. If you set it to D, you press D, set your look vector to be right. If you press S, your look vector should be minus up. And if you press it A, you are minus right, sort of thing. All right, so you can figure out your look vector depending on how your character or your player moved. Oh, yeah, this is the NPC, so you wouldn't be pressing you'd look at, whatever motion vector you had. Maybe it's according to the algorithm. If it's a kinematic body, your algorithm, you're working out, how you want it to move. So therefore, use that move vector to figure out what that look vector is. So we do a shortcut. We say, whatever direction it's moving in, use that as the look vector. That look vector. Always look forward. Right. So that's the math for today. Is anyone did that's mind-blowing enough? Is that, thankfully, despite all of the stuff that I just drew on the screen, the implementation is much simpler. It's more just, it winds up being like this. It's really a matter of determining what is this direction that it is moving in, right? If it was a NPC that was controlled by, just rotation and movement, rotate it and then push it in the direction of up, then this just works. If it's in the case of something that move, kind of directionally, then we have to kind of, if it can't rotate, we have to figure out what this would be and not use that. All right. So let's get back to there. Now, I almost forgot to mention this. Okay, but this is cool, but it is not sensitive to occlusion. What is occlusion? Occlusion is when you can't see something. Something occludes something else. Something gets in the way, right? Your vision is occluded by a wall, or occluded by another enemy, or occluded by a cloud. It's the thing that hides it, right? So if something is hiding behind something else, this math is not going to tell. Because why? Well, because it's just point and a point. Whoops. There's just 2 points, and we're just doing the math based on there. It has no idea of the physics. It has no idea of the obstacles in between. So for that, we need to rely on the physics engine more, the stuff that's going on, the collision part of the physics engine. And we say, okay, let's look for things that the view could collide with. All right, that's where ray casting and its sibling line casting come in. Now, there's also some other types of casting. There's circle casting, and I think even box casting, which allows you to basically put something in the scene. Like it could be a ray, it could be a line, could be a circle, could be whatever. You just kind of cast it, throw it into the scene. Maybe it's along a path, right? You cast that object, that shape into the scene, and you see what it hits, right? It's like casting a fishing line, casting a net. So you're casting something and you see what it hits. So this is useful for finding colliders. And it finds what colliders are hit by an imaginary line from a point in a direction. Okay. So we're going to have a point and a direction. That's raycasting, a point and a direction. If you want to draw a line between 2 points, that's called a line cast. So then you can have a line that starts at one point, goes to another point. It'll tell you, okay, what things do you hit as you move along that line? That's the line cast. Okay. So this is useful for the other part of the equation in terms of sensing the player there. So you want to see what objects potentially occlude others, right? When is an object hidden, right? So for example, here we could say Raycast Hit equals, and we use the raycast, and we use our current position, our target vector, right? Of ray is a position and a target. It's not a start and an end point. It's a target and a position. And then we tell it how long of a ray to shoot. And this is the weird part. This one left shifted by 8. I'm going to show you a better way to do this. This last part is something called the layer mask. We've seen layers before in terms of our layers to figure out, physics collisions. We had that layer matrix, and we set layers for objects. And this basically is a way for us to tell the casting engine what layers we are interested in the collisions for, right? This is a old version of it where before I was using some functions built in, so you had to do it a little bit more hand. And then you could say, oh, okay, is the thing I hit the player? And if you hit the player, great. If you didn't hit the player, okay. If you didn't hit the player, well, then you must have looked at a wall, and so therefore you don't see the player. All right. So we combine the two, right? We have this notion first to see, okay, what direction is our NPC facing? And then if it's facing in the right direction, can we see it? Can we cast a ray that actually hits the player? Right. That's the other important part. Right. What order do you do those in? Well, here I'm doing the dot product first and then doing the raycast. You theoretically could do the raycast first and then check the dot product. So it's kind of, it's an optimization depending on how complex your world is, right? You can always say, okay, is there a clear path between the NPC and the player? Okay, establish that first, and then say, all right, is the NPC looking along that path, or vice versa, right? Is the NPC looking in that direction, and then is there an object in between? So you combine the two, you wind up getting something pretty compelling. All right, so let's do that piece of it. Okay, we're not going to move. Yep. Question. The dot product is a pure mathematical thing, right? So just remember the dot product is strictly a function on 2 vectors to say, okay, how similar are 2 vectors? Has no idea. The other stuff, casting is more a game engine kind of deal. Right. Anytime you hear ray casting, it's not ray tracing, ray casting, line casting, circle casting. This is a game engine feature that allows you to kind of, use the physics engine and the collision engine to kind of tell you what collisions are going to occur along that path. All right. There is, yeah, it's the ray casting says there is a line of sight, right? There is a line of sight, and the dot product says, okay, and the NPC is actually looking in that direction, right? That's why you need them both. Because otherwise, if you just take one, if you just took the dot product, you'd see through walls, right? So that would be a problem. And if you just used the line cast or ray cast, you could see all around you in 180 degrees because it has no idea, it has no concept of what direction you're looking in, right? It just looks potentially at a line all around it, right? Because we can only cast one ray, we have to know that ray is within the cone of vision. So we have to kind of put the two together, right? We don't want to cast tons and tons of rays, which is going to, basically bog down the engine. Ray casting is potentially an expensive thing to do. So we don't want to do too much ray casting. So the dot product is nice because it is one calculation, tells us, general idea that it's facing the right direction. And then we just cast a single ray to get, okay, is there line of sight? Right. So what I'm going to do now is I'm going to totally scrap this little mole character here. Or at least I'll hide this mole character, and we'll recreate the mole character. So the mole is from Tiny RPG Forest Sprites. There's the mole. I'm going to use the mole's idle front. Okay, so mole idle front. And drag him into the scene. Drop him. I'm going to drop him up here. Okay, I don't see him immediately. The problem is that he's dropped in and his order and layer is set really low. So I'm going to set the order and layer to 4 so he will be visible there. Okay, let me scale that one down so you can see him. So there's the mole. There's the mole up there. All right. So for now, the mole just has a position. Okay. It's really just a thing. It's just there. It has a, we can see it, and it has a position. So let's start off, and we're going to learn a new debugging technique as well. We're going to start off to say, okay, let's figure out, is there, so we assume that the mole is, for starters, we're going to say the mole is pointing down, right? That's going to be the starter, right? Assume that the mole is pointing down. So let's write some code. Let's do this in code. We're going to call this NPC, well, we'll call this mole vision or mole behavior. Yeah, I always change my mind at least once, at least twice, maybe. Mole behavior, create and add mole behavior. So now let's look in Visual Studio here, and we will close that extra Visual Studio. There we go. All right, mole, where's mole behavior? Didn't load it. Sometimes it does that. All right, mole behavior. So we have start, we have update. In update, we're going to say that we know we need to find a target vector, right? We're going to have the target vector, which is the vector that points from the mole to the player, right? Target vector. How do we create the target vector? Well, I mentioned this in the slides a couple of times. Target vector equals the player's position, right? And to find the player's position, we're going to say game object dot find, and we've named him hero in here, right? That'll find the hero dot transform dot position. I'm just doing this the simplest way because I don't want to spend too much time. So we have the position minus the transform dot position of the NPC, right? Subtract those two. I now have, I got something on my screen. What's that? I do have something on my screen. Where's that, a dead pixel? Oh, no. That's the funniest thing. I was about to drive myself crazy. And yeah, it was a pixel left over from my graphic that I drew there. Okay, sorry, sidetracked. All right, so we have the target vector now. We have a target vector. Now, you're gonna just love this next thing. Now, remember we had debug log, right? We had print debug log. So something very, very useful is this thing called debug draw line. Oops. Draw line, okay? And what draw line will do is it will draw a line from a point to another point in the scene window so we can see what's going on. So what I'm going to do is I'm going to draw from the NPC's location to the player's position. Okay. So that's going to draw a line that represents, whoops, what's that doing there? Okay, that's going to draw this line which represents this vector. I could have also said draw, I think I said draw ray. That was a valid option, but let's just do this one. So we save that, go back to our game. Hello. Sometimes it just takes a minute. There we go. And let's look now what happens when we hit play. If we didn't make any mistakes, there should be a line drawn from the mole to the player. All right. Well, not in the game window. So we'll say, let's see, maximize on play is turned off. It's only going to be in the scene window, right? That's where all our debugging shows up, either in the console or the scene window. All right. So debug stuff is there. Just, oh, look, we have this line. Sure enough, there's a line drawing there. Now, for debug purposes, I have some other things as well in there, which is all other things that can see the player, right? So I'm drawing this line between the two. And if I were to move, I'll move the player here. You'll see the line follows. See, I'm getting more and more lines here because more and more spiders can see me as well, which is freaky. So hide again. All right, so I have a line that shows what that vector is. So now that is saying that's not the line of view. That is just an ideal target. That's just saying, okay, that's the line in between. But we're also saying that the mole should only be looking down, right? I shouldn't be able to see, I shouldn't have this line the moment I got behind the mole, right? You see, like the spiders, for example, the line isn't always there. So up here, if I were to come up here along this, I should be able to sneak up on the mole, right? Here, there shouldn't be a line because it shouldn't see me. I'm not behind its peripheral vision here. All right, so how do we do that? We say that the other piece of it is now it's the dot product that we want to say. All right, so we say if vector2 dot product dot. Okay, and this takes two vectors, right? The left hand and the right hand. And we're not going to worry about this too much because it works out to be the same in terms of which one we're comparing. It doesn't matter. So we're going to compare what? We're going to compare target vector dot normalized, because we want to normalize its length to 1. And we want to compare that to another vector. And the other vector is going to be transform dot up dot normalized right. What is it complaining about? It is saying cannot implicitly convert from type float to bool. That's right. We're not there yet. But what I'm going to do now is I'm going to negate this, right? I'm not going to look up. I want to be looking down, right? So I just take the negation. That means point down instead of up. That's going to give me a number between -1 and 1. I'm going to say, all right, if it's greater than 0, draw the line. And I'm going to say float. And we'll go back to Unity. The moment Unity stops thinking about the other stuff. Come on, Unity. There. So now let's sneak up on the mole. And here we go. All right, the mole can see us. We're in front of him. We're in front of him. And now he can't see us because we are behind him. Okay. So as long as we are out of, we assume that the mole only has 180-degree field of view, which is pretty good for a mole, considering they're supposed to be practically blind. So maybe the mole should have a very narrow cone of vision. So what that means is we just increase this number. We say, oh, okay, the mole can only see us if we're, say, almost directly in front of him. So, yes. 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 Your player, yes. Yes. or whatever it is, whatever the object that you want to see, is it looking at it? Maybe the NPC should be looking at, something else on the screen. I don't know. It could be whatever you need it to be. But in this case, it's the player. Now you watch. The moment I get like right in front of him, he can see me. But I get a little bit out of his field of view, and he can't see me. All right. So that's good for there. But now the question is, okay, say I was in front of this wall. There's this wall here, right? Now he's seeing right through that wall, which is no good. That's no good. So next thing we're going to do is we're going to build the line cast piece of this in. So, and the reason we have line cast and raycast, now line cast is good to know in this particular case because we know there's no reason to look behind the player, right? We're only interested in the line of view up until it hits the player. So that's the hint that we can use a line cast for this. So I'm just gonna put it at the bottom. I'm just gonna start typing here. So we're gonna say, and this is a physics, this is something provided by the physics engine. So physics 2D line cast, and you'll see it has a start point and an end point. So similar to draw line. We'll take those two parameters. And it will draw. Now, at this point, it is going to assume that it's looking at everything, right? It is looking at everything. So the problem is we only want this to be true if the player is the thing that it is actually looking at, right? So let's see. Let's think about this. All right. So we have it intersecting with anything, but what we're really interested in is the player. So let's. The good news is this is a weird thing. This returns this thing called, it's a good good thing. It returns something called a Raycast Hit 2D, which has lots of information in it. But one of the cool things about this is you can also treat the results as a Boolean, as a true false. You could say if this hits something, right? If true, it hit something. If false, it didn't hit anything. Right. So we can have it. I'm going to have another line here. If it hits something, draw a line between that. And that's not exactly true. We're really just interested in the player. Did we hit the player? How can we, we don't want to hit anything. So here's where that thing, the layer mask, came into question here. So watch this. Ready? I'm going to put a comma here, and immediately it says, okay, you're not just using the version that says start and end. You're going to use the version that says layer mask. Okay. So we can say, I believe physics 2D dot get layer. I'm gonna get the let's see over here. I think layer mask get mask. I'm not using physics 2D. I'm using layer mask. Layer mask get mask. And in this case, the only mask I'm interested in is actually the player. That's the thing I want to try to hit. Now, that's potentially problematic because I don't want to only see if I hit the player, because I want to see, do I hit other things along the way? Right. So that's no good. That's no good. So basically, what I'm really interested in is anything other than the player. So maybe there's a way we can accomplish this. Now, so let me make sure. Now, this is the player's layer here. So hero is on the player layer. All right. So I'm interested in anything but the player, right? Because this will tell me, did I hit the player first. No, this will tell me, did I only hit the player because I didn't bother looking at anything else? That's the problem here. All right. So if I do this, no, is that bitwise XOR? That's what happens when I'm thinking on my feet again. I was trying to like optimize. Bitwise. Yeah, that is bitwise negation. This is one for you programmers here. The little squiggle here, bitwise negation operator yields the bitwise complement of the operand. In the binary representation of the result, every bit has the opposite value of the same bit and the binary representation of the operand in the same way. Okay. So this means that every bit except for the player's bit in the mask will be set. So this is fancy. This is the one hack of the day to say, okay, find, did it hit anything other than the player? Now you might, if you wanted, we could also say, did it hit, we could maybe here's another way of doing it that's not quite so fancy. If I said this, we have a layer called obstacles. And we also even have, we're going to OR this with a layer called what? We have, let's see, the obstacles layer, obstacles. And then if we choose one of these orcs, you'll see the enemy layer. So really, if we hit an enemy or we hit the obstacles, that works too. All right. So now that's easier than that whole bitwise XOR thing or bitwise negation thing. For those of you who are computer science majors, want to remember about bitwise operations, remember that. Otherwise, for those of you who don't remember all that, and this is one of the cases where Bolt has some shortcuts to make this even easier. But so we have a layer mask. We're saying, okay, the layers that we are interested in the obstacles layer or the enemy layer. If we hit either of those two things, this is going to be true, right? And the reason we're using line cast is that we have a line that is directly from one to the other. So we're only going to see as far as the player. So it'll tell us anywhere along that line, we're going to draw that. Now, another cool thing about debug draw line is you can specify a color. So I'm going to draw a red line if the line in between is clear line of sight. Right? Did I do that? Sorry, I wanted to say if not that. Okay, meaning it returns an empty, the line cast did not hit anything, on those two layers. Make sure to save that. This is one of more sophisticated things that we might want to do it here. That's why it's AI. AI is supposed to be sophisticated, right? It's supposed to be fancy. So now, let's see. Here's the big moment. Application reloading. All right, so we're moving. Ah, red line. But if we hide here, look, no red line. We get a white line. Get the white line when the field of view is there. You get the red line when there's a clear line of sight. So now we just have to combine the two together. All right. So we'll come down here. We're going to say, all right, if How do we combine the two? Well, we're just going to put them within there. So it's going to say if the dot product is greater than 0.9, meaning, okay, we're in front of you, it's going to go ahead and draw that white line. And then it's going to say if you didn't hit anything, then draw the red line. There we go. One more. All right. The miracle of editing, that didn't take any time at all. Wish it wasn't editing. All right. So let's see. We're only going to get a red line when we are visible to the mole now. So player comes up. We're within line of sight, except we know his vision sucks. So you see it only turns red when we're right in front of him. And it doesn't turn red if we are on the other side of this wall. Okay, we get the white one, but not the red one. We're in the line of sight, or we're in the field of view, we should call it. One's the field of view, the other one's line of sight. We're in the field of view, but not within line of sight there. All right. So let's do something useful as a result of that. This is going to do something useful. So instead of just drawing a red line, we're going to want to move the mole. We want the mole to move towards the player. So here, we're going to check another box. We want to use interpolation, the magic of interpolation, to get us there. All right. So if I recall, vector 2, move towards. Now, we could use lerp, we could slurp, we could do any of those things. This is basically a shortcut to between two vectors. You see this maximum distance delta, right? So we're going to say we want to move from our position to the hero's position. And some maximum amount. So we'll say, well, for now, we'll say 0.2. All right. So this will return that, but now we also need to remember we need to make that assignment. So we say the new position of the mole should be moving towards the player. Now you have to be careful because this might, in fact, run the player over, right? Because you keep moving towards him, never stopping, right? It's our Zeno's paradox sort of thing. We're going to put that into action here. We're interpolating by moving towards it a little bit of the way every time, subject to some maximum distance that we set. Okay, do your thing, Unity. I hit play too quick. Possible. All right. I hit it again. All right. So our player moves up. Our player comes out. Now, it's kind of tricky because the poor mole can't move any closer to the player. So the mole, that's about all the mole can do because his field of view is so small. Kind of a bummer of a character, isn't he? But he does move rather quickly. So let's click on the mole here. Let's try to get him to do something a little slightly bit more interesting by moving him somewhere. Put him over here. All right. And now let's take the player you'll see the mole is very quick. The mole is right on top of him. The only thing you can do is like move backwards, and it'll leave the mole totally on his own there. Again, let's try to move. You'll see the mole just right on top of him. So the thing to do is adjust the mole's movement, and you'll notice it couldn't move anywhere other than a straight line. So let's make the mole a little fancier, and we'll slow the mole down first off. We'll just say you can only move 0.1, and this move towards, wouldn't it be great if this direction that the mole was going to move, or we could assume that, okay, anytime the mole sees the player, that's going to be the direction the mole then looks in, right? So the mole will see the player within its 0.9 degree, sorry, not 0.9 degree, but it's within its limited field of view. But then it will constantly assume that it is looking at the player at that point. So it'll change its field of view. So instead of just being this, what was it? The negative transform. So the down, we need to change it. We want to change it to be that new position. So what we'll do is we're going to create this look vector, vector 2, look vector. And for starters, in the start routine, we're going to say look vector equals, and this would be the way that it starts off looking. Okay. So we can say here, look vector. And then we could say, okay, if the player sees if the NPC sees the player, that should become our new look vector. Right? It's the target vector. And we'll normalize it. So now the mole should be able to kind of wiggle around and look to see, where it is. And let's even do it. Let's do it after that, because we'll do it after the motion even. So we'll make it kind of extra smart. Should we recalculate that? I guess we'd have to recalculate that at that point. We would have to say, so yeah, we're recalculating the target vector based on this new position of the mole, and saying, okay, now the mole points from where it currently is to the player, and that is the way it is looking, right? The look vector is now that target vector. So let's see. And let's make it, let's try to slow him down even more. Pretty slow. And that movement might be the sort of thing that we want to multiply by time dot delta time. So that's what we get for prototyping fast. So I'm not going to be so concerned over there now. Maybe now, since I've sort of hopefully convinced you that would work, let's pay attention to this screen over here. And let's see. Now you'll see down here, there's the mole. And the mole is giving chase there. Now I managed to change directions fast enough there by kind of backtracking. Oops. Because the mole had such a tight field of view, at some point you can kind of sneak past him again. If you let him chase you, he will chase you. All right, let's do maximize on play so we can get a real good feel for what he's doing there. Yep. Well, the cool thing about this, you'll notice the mole itself really doesn't have much of anything on it. We're just using the mole idle front. This is the one here, right? Mole idle front. It just has a sprite renderer and that script at the moment, right? Because we're using, this is not even using kinetic rigid body or anything like that. We are just directly manipulating the position of this mole. We're entirely scripting its motion. There's no physics involved in how this guy is working. Right? So that makes it. Oh, all right. Well, let's go back. Right. So there's nothing on here that's saying, there's no physics, no rigid bodies. So to get it to move, we can always directly manipulate the position of an object. Right. And we manipulate the position of an object by changing transformed opposition for it. Wow, he's kind of in a stuck position there. That's silly mole. So let's look at the script again. So okay. Well, the important thing here is that this part here, you're not getting. Are you getting this any lines at all? So let's start here. Let's walk through it again. Okay. So this is using, again, this is not even using really the kinematic rigid body. This is using the kind of simplest brain dead motion here. All right. So we start off. We want to figure out, based on where this object is on the screen, we want to figure out the relationship between this object and the player object, right? So we want a vector that's drawn between the two, right? So we subtract the object's position from the target's position, which gives us a vector that points at the target from that NPC, okay? That's the first thing. Then we say, okay, if, and we dot product this target vector, which is the one we just created, to this look vector. That's the direction that we assume that this NPC is looking. We set it up to be, for starters, the look vector is looking down on the screen, right? Negative transform.up normalized. So that means pointing down. Otherwise, if it said transform up without the negation there, it would be pointing up, right? This normalized is actually sort of extra because transform.up actually, I think, is always just a normalized. So we're just being extra careful there. So that is supposed to determine, is this NPC looking in the direction of, is it the field of view between the NPC and the character, the player, right? This piece. So then we draw a line just to indicate, draw that line from that position to that position, right? It hasn't moved yet. The next step is to use our line cast. And the line, we're going to cast a line also from the position of the NPC to the position of the player. And we're going to ask the line cast to say, do we hit anything that is on the obstacles layer or on the enemy layer? Right? And we use this not, right? We could say, if this, another way of putting it, equals false, right? That would say this did not hit anything on the obstacles layer or the enemy layer. I could put a bang or a not in front of it, or I could just say, okay, is it false? Right? And then if it didn't hit anything, that means that we can see the player, because the line in between the player and this NPC is clear. There's nothing else hitting it, right? So this assumes that the player is on a layer other than obstacles or enemy. That's the important thing. And the other thing that's potentially sometimes is challenging about this. Okay, if you're not careful, if you put this character, if we put the mole, and this might be what you're encountering here. So say the mole was here, and we put the mole on the enemy layer. Now, this may or may not be a problem. In this case, it's not going to be a problem because there's no collider on the mole, I don't think, at this point. So I think it's going to have a problem. So let's see, let's zoom back out again. So our mole should still see us here, I think. Yeah. Oh, what happened, mole? Oh, I know what. There's another bug that happens occasionally. Well, we'll fix this one. All right. So does that are you still stuck? Okay. So okay. So do you get a white line at all? No line at all? No line. All right. So do you double check this to make sure that you have, are you getting any errors in your console window saying like, oh, I can't find a hero, I can't find a player, I can't find am getting what? An error? Okay. Well, what I would then, first thing I would do is, okay, so you can always do this. You can say, okay, before you get to any of the smarts, because we can even, all right. All right. Well, magic happened. Okay. So the one thing that can happen here, and this is a fun one. Occasionally, if you wind up that this, you can wind up with the look vector being, if this target vector, you basically wind up with this being 0, right? So it's possible for this target vector to wind up being just you were on top of it. You kind of like drove the poor mole nuts, in which case it saw you inside of itself, meaning the target suddenly became 0. And so that's sort of a problem. So what I would recommend is you say, okay, if this gets around it, you could say if target vector dot normalized dot magnitude greater than 0. So this is sanity check here for the mole. This literally is a mole sanity check to say, oh no. Nothing can be inside your head, mole. So if you only are interested in looking at things outside of your head, right? So this is, think of it as AI for the mole, right? No, you're not going insane, because if you thought that the player was inside your head, that would be crazy. So this is sort of what this is saying. It's saying, okay, there has to be, you will reject any inward looking, location, and that should probably solve your issue. I think it'll solve mine as well. Okay, so now the mole will be a little bit more sane in that regard. All right. So we'll come over here And yeah, it was used to. It was a feature, I suppose, a feature of the game. I used to have these guys where you could run them over and you would basically drive them insane. They would say like, "Oh my God, and then it would just stop. So now you'll see. All right, it assumes that this was the direction. You can't turn them around, so it's a kind of a way to cheat the mole as well. You could say, okay. If you hit him at a certain angle and then move away at another angle, you can kind of cheat him. Oh, and if you push him up against a wall, you can do stuff to him too, I guess. The mole is mole's field of view is working against him there to kind of make him, vulnerable. So you play around with different values there, right? This the AI in this sort of enemy AI is not a, it's a creative license. It's basically creating a behavior. It's you need to kind of tune it. You need to say, well, okay, how should it be? And should all characters react the same way? Should they have different fields of view? Should they move faster? Should they move slower? And so on. All right. So this is a really aggressive mole here. But, so he's going to chase and chase and chase no matter what until I maybe managed to get him up again accidentally, even though you get him up close to something and suddenly he just can't look around. Silly mole. But let's look at these other guys. Now they have a much wider field of view and they move much more slowly, and they're kind of dumb in the case if they bump into anything, they die. So they have that working against them. And their look of view is always changed according to the direction they're facing. So if I come around here, sneak up on that guy as well and stomp on him. So that's the basis, the kind of the fundamental basic thing of simple 2D AI like that, right? It's a matter of establishing a field of view and then a line of sight. Okay. You'll notice all the other characters in here, though. They do, even when when they don't see something, they are kind of bouncing around, moving around, doing some stuff, kind of, whatever. And that's kind of cool for them. All right. So the question there is, well, how do they deal with things? And potentially, what is that spontaneous self-motion? How does that happen? Okay, there's lots of ways you can do that. The way that I'm doing that in here is I actually have a second script on each of these objects. If I look at my orc, it's the orc player, orc prefab, sorry. If I look at the orc prefab here, it actually has, and I did this with a flow machine. So let's look at the walk towards flow macro for those of you who might be interested in Bolt. And this is what I mean by things become spaghetti. Slightly different. It looks more daunting than it is, but it's always the problem. And this is doing more than the other one. This is actually handling the animation, setting the animation state as well, and also taking care of when they die. So this is like when it dies, and this whole chunk down here is animation, this part over here. And so the other logic is largely in here. And the problem is like every time, getting a variable, and the other one where I just said equals this, I need to get a variable for that one. Like doing a simple subtraction, there's a box for that sort of thing. But largely it's the same sort of thing, right? I am stepping through, I find the hero. Once I have the hero, I get the transform of the hero. And I also, let's see, then I have a line cast here between the hero and let's see, that is the position of myself, right? So it is the same, it's almost the same code. It does the, because you can never have too many ways. Let me show you where the why there's another way, why this is a potential bug here. So let's close Bolt or at least put Bolt on the other screen again here. Now, so we have the mole, and let's do something. Let's think about how can we kind of randomly move the mole a little bit. So to randomly move the mole, we need to have some sort of rigid body on it if we want to like move it with physics, perhaps. Because if ultimately the orc or the goblin or the rogue, whatever you want to call them, it moves randomly. All of the other creatures move randomly by basically every 2 seconds, I add a random force to their rigid body. So this Bolt code looks a little bit easier to deal with, right? You have a random, let's do it this way even. Maybe if I line it up, it'll be less daunting. Yeah, that looks way more understandable, sort of, except for that recursiveness here. So it waits 2 seconds, generates a random number, generates another random number, puts those 2 random numbers into a vector, and then uses that vector as a force to add to the current object, or the rigid body of the current object. Right? Every 2 seconds, just gives a kick in a direction. You notice it's just a little impulse, and it just kicks itself, and that just randomly moves around. Then, if it sees the player, it corrects all that and then does its normal thing. So it sort of puts itself at a little bit of a disadvantage using that. So say we were to do that same sort of thing. We want to do that for the mole. So we go over to here, mole, and we'll call this mole main or something like that, just so we remember which one it is. Mole man, maybe. All right. So let's assume we need to add a rigid body to this. And this will work out, rigid body 2D. And the first thing we're going to do is we're going to say, okay, there is no gravity here. Right? And all right, so now if we were to manipulate that rigid body, it would potentially move, right? And if we don't manipulate it, it's just going to sit there doing nothing. We could run the player up there. Let's see, we'll run the player up, and well, we can't collide with it because it has no collider on it. So right now it's not really capable of much of anything other than its normal movement. Okay. So let's stop that. And let's add that random move here. All right, so random movement. Back in the script. For this, since I know, just for now, I want to do it based on a set interval every 2 seconds. I'm going to say void add random force. And I'm going to do that every 2 seconds. So I'm going to do that with an invoke. Right? Invoke add random force. Well, actually, invoke repeating, I guess. Yeah. Every 2 seconds, add a random force. And we're going to happen immediately, and then start adding random force. There we go. So, to get a random force, we are going to say, we're going to say transform get component rigid body 2D dot add force. And the force is going to be a vector 2, which is a force. So let's add a random force. So new vector 2, and we're going to give it a x and a y. So what are we going to use for that x and y? Well, we're going to use random random range. Well, I'm going to use random range, right? Because I want it to be between -2 and +2. Okay, so because I want it to move in any direction. So that's my random X, and my random Y will be similar. And we'll make sure that these are all floating point numbers. There we go. So transform get component rigid body 2D. So we say get the rigid body that is associated with this game object and add a force in that direction, a random direction, right? And we'll do physics 2D, or no, is it force mode, right? Force mode 2D dot impulse. I know, remember our discussion on impulse, but anyway, there we go. So this will, every 2 seconds, add a random force to the rigid body that this player has on it, or this non-player has on it, right? So ready? Here we go, Mole. Hit play. What time is it? 4:02. Okay, so the mole just started randomly moving, and it actually just randomly ran off the side of the screen. That's not great. Just randomly ran off the screen. No good, no good. All right, so we need to keep it on the screen. So therefore, what we should do is we should put a collider on it, so it'll collide with these boundaries. Good idea, right? So MoleMan, add component, collider, and we'll use a capsule collider 2D, and we will take a look at it. And sure enough, tighten it up, reasonable. It has a capsule on it now. We'll hit play. Now it should not be allowed to go through objects that have colliders on them. Right? So it rotates, it acts a little bit silly. All right, so be it. Now let's see. Our mole. Our mole is very silly. Let's fix our mole a little bit. So the first thing we're going to do is we're not going to let the mole roll. No rolling moles. So we're going to change the constraint and say, okay, don't do any rotations that way. All right, mole, that's better. And this random motion thing might be too much for the mole because his vision is so bad. All right, let's see. You'll notice the mole is not really chasing us. Now, let me put maximize on play. I'll turn that off. I'm going to use my debugging now. So in here, and here's where it gets a little bit tricky. So I've got my, got my player. I'll move this over here and let's see. All right. It's within the field of view, but you'll notice it didn't detect a clear line of sight. It never went red. Now, why is that? And this is one of the trickier things about line casting and ray casting. So it couldn't see the player because it saw its own. This is the groundhog effect. Okay, this is a mole, but not a groundhog. But it's got the groundhog effect in which it has seen its own collider. Right, we had that collider around there. We did that raycast, and the problem is that we saw that collider there. Right. Now, how do we deal with that? How do we deal with that? There are a couple of ways you can do that. You can do things like, for example, you could get fancy with your math here and say, well, don't actually draw the vector from the center of the mole. Instead, shorten that line somehow, push it outside, add something to it, along that vector, right? So maybe, we have this target vector. That's the position. So what we could do, we know that's the direction between the two. We don't want it to start on there. So this is the kind of crazy things we have to do, is we'll say, all right, when we do this, don't draw it from this position. Instead, draw it from that position plus the target vector, which is the target vector normalized. No, let's normalize the target vector. Just maybe we should have normalized it to begin with, but normalized. What happened here? Target vector normalized. So what this is doing transform position. Which one is which here? Vector 3, vector 3. So we can cast that as a vector 3. So what I just did is I needed to convert, because this addition here needed to be fixed. And so I made this vector 2 into a vector 3. So take my word for that in here. And we're going to do the same thing. Basically, well, we can use that. Is it really? Yeah, it's really just the line cast that we have this issue with. In this case, I think. So, oh no, I do. Right. Sometimes it doesn't like when you just. So what am I doing here? What did I just do? I said, okay, the position of the mole plus a vector that is 1 unit away, right? So it could be even tighter. So it'd be like, okay, this is 1 unit here. So instead of being from here to the player, it'd actually be from here, which is probably too much. Let's look at the mole. Mole man again. All right. And we can see the height. Let's look at the height of the capsule. So the height of the capsule here is 0.75. So let's make our distance or offset to be it basically needs to be half of 0.75. So it could be 0.4. We're going to offset it by that 0.4. Just a little bit. So we're getting kind of fancy. So normalized times 0.4. We are scaling this vector by 0.4. Right? This is normalized, so the length is 1. We scale it so its length is only 0.4. Let's see if that works. Fancy. It's 410. I've just been cranking away on this. So this is probably one of the fancier ways to do, or one of the more complete ways to do it. You could also, another way to do it is to try to hit the player and ignore everything other than the player. So let's see. Let's see if this worked first off. So there we go. We're moving. Certainly tracking. Oh, and it's pretty far. So if we get really close to him, we can kind of intimidate him and push him away, which is kind of neat. Our point 4 and not quite right. Point 4 from the player. It looks like more than 0.4 there. So we can kind of tune that as well. So this is the position to that position. Position plus vector target. No, that should be right. Target vector normalized times 0.4. Yeah, I think we're good to go on that one. All right, so that eliminated the hitting of its own collider. That's one of the kind of things we have to deal with. Now, on the other hand, what you could do is be fancier about this line casting as well and say, all right, to say, all right, try to cast a line at everything, right? Cast a line at everything. So this requires us to say Raycast Hit 2D, right? Is that what that returns? It returns Raycast Hit 2D. Hit target. Okay, it's another way to do it. Hit target and say, let's try to hit something. Whoops. Hit target equals, just do the whole line cast. And assume we're going to just try to hit everything. All right. So this is going to be a slightly simpler version. We're going to get rid of this plus. We're just going to say, all right, go ahead, hit target. What do we hit? From here to there. So if the thing we hit is the player, that's also good. So instead of all this, we could say, if, first we want to say, if hit target equals true, right? We hit something. Then we want to say, if hit target dot, now we can ask, what did we hit? We can just say collider. What did we collide with? And we could even say name equals 0. We could say, if we hit something and the thing we hit is the player, go ahead and do everything. And that avoids that weird self-occlusion thing. So maybe I should have led with that. I don't know. They say lead with the complicated thing and then show the easy thing when you're done. But maybe this was too much. All right, 4:15. So let's see if this works. And then I'm going to leave it up for a second so that we can kind of see. We're going to step through this slightly simplified version that avoids this self-occlusion issue. So much going on the screen. Let's go get that mole. Mole seems to be running away from us. and too many lines as well. I should turn off all those spiders. So if target equals true, meaning we hit something. And then if hit target collider name. So I'm going to do this. I'm just going to say, just for sake of print, saw the here. There's just so much stuff now going on the screen, and seeing all the lines is a little bit fancy. And maybe I'll do this. I'm going to give him a little bit more line of sight here. So Mole will have an easier job of seeing us. Is anyone still here? Did everyone bail? Okay. Let's get this to work, and then we'll call it a day. This is good. This is distracting me from the election, so that's one good thing. All right, so let's move up here. Let's see the console window. And Mole. The mole can't see us. No, if I hit, well, this is double equals, right? No, this is returning. This is returning the name. You'll see it's returning. This returns a string. So this is a string, and then not in C#. So this should be working. What's going on here? Hit target. Let's first verify that. We'll do it in two parts here. We'll first say and I guess the other question is, how come I didn't even see that line? Oh, what? Let's see. I was hoping there was like a worse bug than that. But. Oh, hit something. All right. So that's interesting. Is it still? Well, it shouldn't be, because I'm saying, okay, that I should. Oh, you are correct. It is hitting its own collider. And let's see. So maybe I didn't work my way around the other one. How did I do it in? Because I did this in the Bolt version, and now let's look at the Bolt version. So debug how would I do it in the Bolt version, and how am I doing it differently in this version? All right. So in the Bolt version, I said, okay, draw a line, casting the line, cast this, I check, I get the collider. If it's not null, I get the game object. So the layer mask I used for those, the layer mask was, that's what I did. All right. So I cheated. Well, I don't know if I cheated or not. I said, okay, in there, I said, if you see the player or obstacles, you didn't care about other enemies. So I eliminated the self-shading thing by not letting it hide behind other enemies. So we'll make that, rather than work it through. I'm sure there's a way. I know I've done it in other versions. But for now, we can say, okay, you're not allowed to hide behind other enemies. That's the easiest way to solve it. And that certainly would be valid. I guess I thought of that the other day, but just couldn't remember it today. So, whoops. So, yes. So in here, the thing to do would be, the simplest case is to come in here and not let, I shouldn't have done that comparison, or I can say in here also specifically to say, is this collision happening? Using the get line line mask. Layer mask. Dot get mask up player or the same thing but obstacles. So let's let it hit the player or obstacles. Those two things are allowed. And now let's let this work. Unity just slows down by the minute, by the hour. 4:23. All right, let's get Bolt out of the way here. Let's get this there. Really just want to prove that the equals works. So. All right, so the mole. Can't see me. Can't see me. There we go. Yeah, it's colliding with itself, and it is a tricky. That one can be a pain. That one definitely is a painful undertaking. The one, like I said, I think if you want to allow it to collide with things other than, like, sometimes, we could play a game where we turn off the layer mask of that as we're trying to detect the collision. Or I think one of the safest things is often the thing to do is say, okay, check it, like I was doing with the pushing the line of sight to be outside of the thing you're checking, or you just say, these can't see other enemies. So it's always a compromise. If I think of yet another way to do that, I'll illustrate that one as well. But that's the basic of it. Wow, managed to talk that for a long time. A couple of different ways to do it. Review the video again. And have a good election day. And we'll see you all on Friday. Feel free to post questions about that one. Yes, the dot equals, that would work too. That's definitely a way to do it. I guess I'm more from since the string is a class and get is used on there, the equals implies that you're comparing the contents, the actual string, and not the address of the string there. By the way, it's dereferenced there. So, okay. If you have any questions, type them to me. Otherwise, I'll let everybody go. It's getting too late. You guys should get some food. All right. Have a great couple of days. Take care. You too.